Hi, Victoria.
Hello. Thanks for joining. Jesse should be on any moment now.
I can't hear you. Must not have started yet.
Okay, I changed my headphones. Can you hear me now?
I can hear you.
Okay, great. Jesse should be joining any moment.
Great.
And Madeline is also going to let everyone know that we're recording when she does the
Perfect.
intro.
Victoria and Bev, I can't hear you. I don't know if you can hear me.
I can hear you. I will chat that. I could hear everybody. I had the same problem.
Well, I'll log out and try again.
Well, actually, before you do that, maybe turn up. Hi, Jesse.
Hello.
That's a nice landscape.
Oh, thank you.
It looks barren though.
Yeah, it's I don't know if you guys have been there before, but it's in Hawaii on the Big Island, and it's I went there for a GSA field trip. So it's actually my photo, but you know, there's a bunch of active sort of lava breakouts there, and you can stick your rock hammer in them and make your own rock. And
Is that the new eruption from just a couple of years ago?
Yeah, well, we walked across parts of it. I can't remember if what we're seeing in the photo is, but if it's not, it's really close to that big eruption that happened a few years ago. Yep. It's like Madeline's.
Is Madeline able to hear now?
There she is.
Can you guys hear me? Because I can't hear you.
I can hear you. Hey, Victoria, can I try something again with my mouse with the share screen, or is it too late for that?
No, you should be able to do that. I've made you host
Okay, yep.
now.
All right, I see. Yep. I just want to see if, because you know when I go into the presentation mode, I just want to know if so can you see that?
I can see it, and so you would just have to start your
Right.
yes.
Okay, so I just want
slideshow.
to test something here because I have two screens. So
Okay.
you can see my mouse now on the car, right?
On the back end of the car, yes.
Okay, I'm gonna try my other screen. Can you still see my mouse?
I cannot.
Okay, all right. So now I know which screen to point to. Thanks.
You're welcome.
But your screen is looking like it's in a viewer mode, not in a projection mode.
Oh, okay.
Because I can see both the chasing the ancient volcanic firestorm and a thing next to it that shows a bunch of cars and says needs a fast moving.
Oh, okay. Uh-oh. Okay, we got
If
a
you
problem.
want to put it up and you want to share the part of your screen that's in the slideshow mode.
Okay, let's see here. I wonder. Did I give a different result, Bev? Or does it look the same?
Just a second. Let me, I was trying to, that looks good. That's perfect.
Okay.
But now you should use your mouse and we can make sure we can see it.
Can you see my mouse now?
I can see mine. I cannot see any mouses, any mouse of yours.
How about now?
Yep.
We can see it, yeah.
All right, perfect.
So,
So our introducer may be having some technical difficulties.
we could hear her before. So what do we want to do?
I guess if she can't get on, Bev, would you be able to do the introduction so
I
Jesse
guess.
can go on?
Yeah, just a second. Okay. So did Madeline just go off again?
Yeah, I don't see her as a participant any longer.
So
So
do you want me to introduce? So I'm Bev Hartline, and I'm the Vice Chancellor for Research and Dean of the Graduate School at Montana Tech. It's a great pleasure to host a Zoom public lecture by Dr. Jesse Mosolf. He's a field geologist at the Montana Bureau of Mines and Geology. And importantly, he was the MBMG winner of the Distinguished Researcher Award for 2020, so last spring. I actually don't know when he arrived at Montana Tech, but it was on the order of a half dozen years ago. And he focuses on Cordillera tectonics using detailed geologic mapping, microscopy and radiometric dating and modeling. He's done a whole lot of field work, contributed to a whole lot of maps, geologic maps, the 7.5 minute quadrangle maps for the state of Montana. He got his bachelor's degree in chemistry from Montana State University in Bozeman and MS in geology from the University of California, Los Angeles, with a PhD from University of California in Santa Barbara. So please join me in welcoming Jesse to talk to us about chasing an ancient volcanic firestorm in the northern Cordillera of Montana.
Okay, thanks, Bev. And thanks for the few of you that are tuning into this on post, well, I guess it's still kind of election day. Yeah, so today I'm going to talk about chasing and like Bev said, chasing an ancient volcanic firestorm in the northern Cordillera of Montana. Kind of a dramatic title. It's hoping to draw some people into this topic, which I actually find pretty fascinating. And to chase an ancient, slow-moving or a volcanic firestorm moving at geologic sort of timescales and paces, need a fast-moving jalopy like this car you can see in the photograph. In the background, you can see the Dillon volcanic rocks here, or volcanic rocks of the Dillon volcanic group that I'll talk about later in my talk. Okay, looks like we got a little bit of a delay, I think. Try the. There we go. Well, I was hoping there'd be more people signed on so I could put in this plug for TRGS, but anyway, I'll go ahead with it. So this, the Tobacco Root Geological Society has an annual field conference. This year it's going to be held at the Lost River Field Station in Idaho, and it's going to be a great field conference. There's a bunch of field trips already lined up, including trips looking at the Challis volcanic group, the Lost River Fault, the McKay gold copper mine, the Pioneer metamorphic core complex, the Pioneer thrust, and craters of the moon, just to name a few. So it should be a fantastic conference if, depending on how COVID goes, if it actually happens. So we're staying optimistic, and it's tentatively scheduled to be held at the end of July. We're working on the announcement now, but it should be posted soon at trgs.org. So check it out if you're interested in joining us in Idaho. And it's open to people of all backgrounds, just not geologists. Okay, so I just want to start off by saying I love my job, and I love my job for a number of reasons. The main reason being that I get to map for the sake of mapping. And so during my career in Montana, I've actually had the opportunity to map all kinds of different types of rocks and within all types of different tectonic environments. That's because Montana's geology is pretty diverse, which is probably not news to most of you. So while at MBMG, I've mapped everything from Archean metamorphic crystalline basement rocks that are billions of years old, through tertiary sediments that you can see down here in the lower right-hand corner, and kind of everything in between, including thrust belt geology and associated magnetism, as well as tertiary volcanism and extensional tectonics, which I'm going to talk about today. And I'm getting more and more interested in these landslide mass wasting deposits we see all over Montana. They're literally everywhere, but especially in the tertiary volcanic and sedimentary rocks. So it was hard to choose a topic to talk about today for this talk, but I decided to go with the tertiary volcanism and extensional tectonics, mainly because that's what most of my work's probably been focused on since starting here, and it helps that I have a bunch of canned slides, and I just got done with field work, so I had that on my mind too. So the work I'm going to show today has mostly been done through the USGS state map program. So I thought I would say a few brief words about that program. So it's a federal program, and it works as a sort of state match, so one-to-one federal state match. And the overarching goal of the state map program in Montana is to provide seamless geologic cover of the entire state at least 1 to 100,000 scale. And as we march along and do our mapping through the state map program, our projects are guided by both societal impacts of the work and potential and scientific goals. And today I'm going to lean heavy on the scientific goals and give you a pretty good dose of that. So in regards to the tertiary or Eocene magmatic rocks that I'm going to talk about today, volcanic rocks I'm going to talk about, some of the goals that we had in mind while working on these rocks were pretty fundamental scientific goals. First, we just wanted to understand or characterize the age, composition, and distribution of the volcanic rocks in Montana, which, believe it or not, in a lot of places hasn't been done in a whole lot of detail before. And then from there, we like to, you know, think about more, I guess, cerebral topics such as petrogenesis and tectonic settings. So, you know, what are the specific origins of these rocks? Did they erupt in an arc-like environment, such as the Cascades of Mount St. Helens you can see in the photo here, or was it a entirely different sort of setting? So we'll touch a bit about on that today. Okay, so here's my talk outline. First, I'm going to talk a bit about the geologic setting in a broad sense, and then I'll discuss the methods employed in this work a little bit, and then from there we'll dive into results and end with some general conclusions. Okay, so geologic setting. I couldn't resist the opportunity to include the geoband in my talk, and so for those of you who aren't familiar with the geoband, it's an old Ford Econoline with a very interesting paint job, and it's a regular at the TRGS meetings. And you know, it actually has a lot of useful illustrations on the van, including an illustration of the Pacific Ring of Fire. Now, I think the Pacific Ring of Fire is, you know, somewhat common knowledge, but I'll say a few words about it. So we're looking here, this illustration on the side of the van. This is supposed to be the Pacific Ocean basin. The North and South American continents are here. And all these red dots are active volcanoes, currently active volcanoes. And a lot of those volcanoes are associated with subduction zones. So if we look at the other side of the van here, we have this nice sort of Geo 101 illustration of a subduction zone where you have oceanic crust subducting beneath the continental margin, releasing water and triggering melting of the overriding mantle and ultimately forming volcanoes in an arc-like fashion. So, you know, not all of these volcanoes are in such a simple setting, but a lot are, including the Cascade Arc that we're familiar with here in our back door. Well, you know, it turns out that subduction along North American continent has been chugging along for millions or tens of millions of years, maybe going as far back as Jurassic or maybe even Triassic time. So that we don't have time to cover that long history of volcanism along the North American continent, but today I'm going to focus on a particularly interesting time during the Eocene. Okay, so this is a generalized geologic map of the Northwest US and British Columbia. All the red polygons you can see represent extrusive volcanic rocks of Eocene, approximately Eocene age as they're preserved today for us to see at the surface. I've also included on this map areas of highly extended terrain that we call metamorphic core complexes, shown by these gray blobs. And there's a couple of things I want to point out here. First of all, I should say that this Eocene volcanic belt that we see with the red polygons, it kind of goes by various names. Most people refer to it as the Challis Kamloops volcanic belt or the Challis Kamloops Absaroka volcanic belt, named after the different fields composing the volcanic belt. And the first thing I want to point out is just how expansive it is, right? It's, in this illustration, we see it stretches from Montana all the way up into British Columbia and maybe up into Alaska. And actually there's Eocene deposits that volcanic deposits that occur further south towards Colorado. Sorry about that. The next thing I want to point out is that in the north, these volcanic rocks tend to form this linear belt. So early workers looked at the kind of the distribution, the linear distribution of those volcanic rocks, as well as the composition, and interpreted these rocks to have been erupted either in a volcanic arc setting or maybe a back arc setting. But as you come south down into the northern US, you see that belt really broadens out and we kind of lose that linear trend. And in fact, these volcanic rocks also become much more alkaline as we come to the south, so much more enriched, which maybe tells us there's some nuances in the tectonics here that are causing both this broad pattern of volcanism as well as changes in the chemistry or composition of the rocks. So people have come up with all kinds of models to describe those relationships. I don't have time to go over all of them today, but what I've done in this figure is I've kind of broken them down into three end member models, if you will. The one at the top, the first one here at the top, this is a pretty popular model where geologists, we think that there was flat slab subduction beneath the North American continent prior to the Eocene, so maybe late Cretaceous into the Paleocene. And well, what does flat slab subduction means? It means that the downgoing slab, the downgoing oceanic slab, was a very gentle angle, and I've outlined that with the dotted lines here. And then maybe during the Eocene, that slab rolled back and steepened up to a steeper angle, which then triggered volcanism in the overriding plate and eruption of these Eocene magmatic centers. And the idea would be that you'd see this sort of westward sweep of volcanism from east to west following that rollback of the slab. The second model envisions the flat slab to break up and founder, and as it's breaking up and foundering, hot asthenosphere was able to upwell, which is shown here by these arrows, which would have triggered magmatism in the overriding plate. And then a third model envisions a slab window passing beneath the North American continent, which again would allow hot material from the mantle to upwell and trigger melting. So most researchers agree that there was probably a slab window that formed under North America, and I guess I should say how a slab window forms. So during the Eocene or early Cenozoic, most people agree that the spreading ridge between the Kula plate and the Farallon plate subducted beneath the margin of North America, which in turn formed a slab window. As that spreading ridge was pulled down, it got pulled apart. Now, what people argue about is where that happened. Was it really far north up by Alaska, or near or closer to Alaska, or was it far south in the U.S.? Brett Sprecher et al., they put the slab window underneath North America to explain some of the alkaline trends in the magmatic rocks we see here. Okay, so taking a closer look at Montana, again, the red polygons show extrusive volcanic rocks of approximately Eocene age. And in Montana, we more or less have, a handful, less than 10 major fields, if you will, depending on how much you want to break these things up. So those include the Elliston volcanic field, the Lowland Creek, the Challis, the Dillon, Virginia City, Absaroka, and then the Alkalic province off to the east, which include the Bear Paw and Highwood Mountains, as well as some other smaller eruptive centers. I've personally worked on a little bit of the Challis, Dillon, Virginia City, and Elliston, and so today what I'd like to do is just share kind of a comprehensive review of what I've learned about each of these magmatic fields in this talk. Okay, so now I'd like to talk a little bit about the methods employed in this work. I'm a field mapper, so it should be no surprise that all of this work is field inspired and based on geologic mapping. We do most of our mapping at 1 to 24,000 scale, which is a really good scale to cover ground to get kind of the big picture idea of the geology, but at the same time, it's a fine enough scale to capture plenty of detail to help resolve geologic problems. For the igneous rocks, well, actually all rocks that we map, but especially igneous rocks, we do a fair amount of petrography, so looking at thin sections of these rocks and looking at what they're made of, what crystals or what materials they're made of. We digitize all of our geologic maps in GIS and synthesize them with the field data we collect. And we do a fair amount of compilation as well, or at least we use previous mapping to guide our mapping. I'm trying to cram a lot into this talk today, so I don't have time to thoroughly review all the previous work. In these, hopefully, I think I might be breaking up a little bit, but hopefully it's okay. I don't have enough time to thoroughly review the previous mapping in all of these volcanic fields, so I've just provided a list here to properly acknowledge the work that came before me that was extremely helpful in mapping these volcanic deposits. So let's move on from there. Okay, so we do a fair amount of analytical work, namely age dating and bulk rock geochemical work. And we're really lucky at the Bureau. We have a state-of-the-art mineral separation facility at our disposal. And that gives us a lot of flexibility for preparing samples for both age dating and geochemical work. So, you know, the work that I've been involved with, I've personally overseen about 161 or I've overseen the preparation of 161 samples for uranium, lead, zircon geochronology, about 225 bulk rock geochemical samples, about 6 argon samples, and about 6 helium samples. I should say that the geochemical and argon samples, what we really did was just chip those and we send those off to other universities. But the uranium, lead, zircon work, as well as the helium work, we prepare the mineral separates ourselves here at the Bureau. We're also really lucky to have a state-of-the-art, or I think a really nice scanning electron microscope here at Tech that we recently acquired. And we have a CL detector on that instrument, which allows us to image zircon grains that we're interested in analyzing. So that's been really great to have this instrument here the past couple of years. Saves us a lot of heartache in this process. And Gary Weiss has been really helpful in getting us online with the instrument. Okay, so for uranium, lead, zircon geochronology, we take all our separates to Santa Barbara and analyze them ourselves. So Santa Barbara has a state-of-the-art facility, and they actually have 2 multi-collector ICP-MS instruments. They're actually split stream instruments. So the one on the left here, you have a multi-collector in the foreground, and then on the other stream, you have a quadrupole for trace elements, and then the mass collector over here is in a split stream setup with a single collector, so you can do a whole array of isotopes simultaneously. But yeah, fantastic facility, and we've had great results using this lab, and it helps that it's in a nice location. So you know, it's right on the coast. This is an overview shot of UC, the UC Santa Barbara campus, and the instruments located about right here. And this is a really nice right-hand point break for any surfers in the audience. Great place to work. Okay, so today I'm going to present about 62 new uranium, lead, zircon ages, and I think it would make for a really boring talk if I showed you all plots of data for all 62 samples. So I'm just going to show you a couple of examples of what the data look like. So this sample here is trachydacite lava from Elliston, and this is kind of ideal sample. And actually, a lot of the Elliston samples look like this. You know, so with uranium, lead geochronology, we're measuring isotopes of uranium and lead. So uranium decays to lead. Kind of the 2 major decay schemes are the decay of uranium-238 to lead-206 and uranium-235 to lead-207. So what's nice about this technique is that you can calculate ages using multiple decays within one sample. And so one really common way to look at this data is on a Concordia diagram. In this case, on the lower left here, we have what's called a Terra-Wasserberg diagram. So we're plotting the lead-207-206 age versus the 238-206 age. And you know, if your sample has not been disturbed in any sort of way, if the isotope systematics have not been disturbed in any sort of way, ideally your sample should plot on this blue line, and that's your age where it intercepts that line. So we plot this data as circles. Those are just showing the you know, two sigma both in the x and y direction. And so you want all those circles to lay on that line, preferably close together for a well-behaved sample. And it might not look like it, but this is actually a pretty clean sample. If we simply plot the 238-206 age as a histogram here, you can see that has a fairly normal distribution, which is what we want. And then from there, we can just calculate a mean age. So each one of these circles represents an individual zircon grain that we've analyzed from one sample. And then we just take a weighted mean of all of those analyses. This is a fairly low precision technique, but you kind of beat the statistics by analyzing a lot of grains rapidly. And you can take a mean of that. And a lot of times we're getting, you know, errors less than 1%, which is fantastic. So in this case, we got a weighted mean age of about 48.21. Okay, but unfortunately, they're all not that well behaved. And in fact, a lot of the samples from Southwest Montana and the Dillon area in particular are loaded with inherited zircon. This particular sample is actually one of my Cretaceous volcanic samples. I didn't have time to make one for an example for the Eocene, but it's the same principles. But what we're seeing in Dillon and most of the igneous rocks we analyze is that we have a whole bunch of inherited zircon. So these are old zircon grains that somehow made it into the melt before it erupted and are not necessarily a proxy for the eruption age. And so what we have to do in this case is we end up having to analyze a lot more zircon than we normally would. Using the CL imagery, you can kind of use that as a guide and try to avoid some of the older grains if you're not interested in analyzing those, but we still get fooled, especially when we're doing high throughput and analyzing 40 samples in one run. So anyway, this is an example where we have all these inherited zircon ages, and we just had to keep analyzing until we had enough of the young grains that we were interested in that were, you know, serve as a proxy for the eruption age. You know, we just kept analyzing until we had enough of those to be statistically valid to calculate a weighted mean age. And in this case, we're getting about 73 MA. Now, I used to curse all this inherited zircon and thought, you know, I just wanted nothing to do with it. But it turns out, you know, well, Dick Berg once told me that that was probably the more interesting part of these analyses. And I think he's right, because it, you know, they might tell us something about what's going on in the crust, or, you know, about crustal structure, I guess, in Southwest Montana. So I've been getting more and more interested in that. We also did a little bit of argon-argon dating. This technique's pretty problematic when applied to altered volcanic rocks, so we generally try to steer clear of it. But you know, it is really good for dating mafic volcanic rocks, things like basalts that you can't really date a lot of the times with uranium lead. So we employ it in those cases, and we've had mixed results. The best results we've had are from Virginia City, which are a little bit younger, on the young end of the spectrum of rocks I'll be talking about today. This is an example of a sample from Virginia City. And in the argon-argon technique, you're basically step heating the sample and measuring isotopes at each step to very high temperatures, well over 1,000 degrees Celsius. And in an ideal world, at each one of those steps, you'd hope that each one of those steps is going to give you the same age if your isotope systematics haven't been disturbed, or if you're not interested in cooling of, say, like a granite. So in volcanic rocks, we want each step to theoretically be the same. That's not always the case, because there's a lot of times these rocks do have some degree of alteration in them, especially the older they are, the more alteration they tend to have. You can see in this sample, we had the very first step, we got this kind of spurious young age, which is probably due to alteration, but the rest of the steps were pretty concordant from one step to the other. So we just take that plateau age, take an average of that, and in this case, we got 33.56. Okay, and then we do a lot of bulk rock geochemistry. We mainly just chip the samples here at the Bureau and then send them to WS Pullman for analysis. Like I said, the rocks are generally have some alteration, so we try to pick the freshest rocks that we can. And our totals have been pretty good. So when you total up the major elements in your analysis, you theoretically want them to be pretty close to 100. This is an example on the left here from Dillon, some of my samples from Dillon, and you can see that our totals are pretty good, anywhere from 95 to 99 weight percent, which is perfectly acceptable, with loss on ignition values of less than 4 weight percent, which, just take my word for it, that's pretty good, or good enough for government work. I shouldn't say that. Okay, so next I'd like to get into some results, starting with the Elliston volcanic field, or group, whichever you want to call it. So this is a simplified geologic map of the Elliston 30 by 60 quadrangle that we just recently published. Katie McDonald at the Bureau's lead author on that map. This is a highly simplified sort of cartoon of that map. Just for reference, to get yourself oriented, Helena's down here on the lower right, Lincoln's up here in the north, Helmville's there, Avon's here, here's I-90 with Garrison in the northern end of the Deer Lodge Valley. Okay, so let's give you a quick overview of the geology. The oldest rocks in this quadrangle are Proterozoic metasedimentary rocks of the belt supergroup that are shown in these shades of green and browns. And those are unconformably overlain by a fairly thick sequence of Paleozoic to Mesozoic sedimentary rocks and some volcanic rocks locally. Together, all these units are generally deformed by contractional structures, folds and faults that have a general sort of northwest strike to them. And then locally, you have Eocene volcanic rocks shown in reds here resting on those contractionally deformed units locally. And together, the older contractional structures and the volcanic units are all displaced by these strike slip to normal faults that again have this sort of northwest structural grain. So why is everything northwest? Well, it's in this interesting sort of tectonic zone that we call the Lewis and Clark fault zone. It's thought to be this long-lived fault zone that's been reactivated through time, a lot of times with shear across it. And you know what's interesting is if you look at some of our fault kinematic data that was collected along the southwest margin of the Avon Valley, you work that up and look at the PT axis, it is pretty representative or at least conformable with a right lateral sort of shear strike slip system in this area. And if you compare the fault kinematic data with recent earthquake data, they look pretty identical. And so that tells us that maybe the state of stress in this region during the Cenozoic has been the same for quite some time. Well, I should say that we've interpreted this Avon Valley to be a pull-apart structure that might have formed during volcanism, Eocene volcanism, or shortly thereafter. Okay, so we did, I should back up. So the three sort of major volcanic fields within the Elliston group are the Crater Mountain, Garnet Range, and Avon. So we conducted mapping in each of these. We probably spent the most time in the Garnet Range, followed by Avon, and then the work we did in the Crater Mountain was mostly campaign style. We collected about 87 whole rock geochemical or samples for whole rock geochemical analyses, and about 26 samples for uranium, lead, zircon ages. Well, we actually collected a lot more samples of that, but these are what we actually analyzed. Okay, so this is the sort of general stratigraphy, volcanic stratigraphy that we came up with for the Elliston area. So I'll just walk you through this pretty quickly. The oldest Eocene volcanic rocks that occur in this region are these porphyritic, kind of conspicuous porphyritic lavas that we dated from 48.21 up to about 46.2 MA. Those are overlain by a series of aphanitic lavas that were really hard to date. We actually didn't get any ages from those. I guess backing up, I should say that the porphyritic lavas only occurred in the Crater Mountain and Garnet Range volcanic fields. And then again, those are overlain by these aphanitic lavas that actually occurred, we observed in all three of these volcanic fields. And then the similarities kind of break down a bit from there. In the Garnet Range, we mapped this small rhyolitic sort of lava dome that we dated at 46. We didn't see that anywhere else in the quadrangle. In the, let's see, in the Crater Mountain area, we get into a whole sequence of these variably welded ignimbrites that we dated at about 39.8 to about 39.2 MA. And what's interesting, if you cruise over to the Avon area, we get into a pretty thick sequence of rhyolite in the Avon area as well, of similar age, 40 to 39.8, with one key difference is that most of the rhyolite here occurs as actual lavas or domes with some intercalated tuffs, but it looks quite a bit different actually than Crater Mountain. In Crater Mountain, we actually have a pretty thick sequence of volcaniclastic sediments preserved that may represent some sort of intracaldera fill. Let's see, what else? In the Avon and Garnet Range areas, the Eocene volcanic rocks are overlain by tertiary sedimentary rocks of the Renova Formation. And we have these kind of strange, enriched or nearly shoshonitic mafic lava flows intercalated with those tertiary sediments that we've dated around 30 MA. Okay, so let's talk a little bit about the chemistry. I'm not going to go too deep into this, but yeah, let's talk a little bit about composition. So we have two geochemical plots here that you commonly see in this type of work. And so the upper plot here is a total alkali silica diagram where we're plotting the sodium and potassium in each sample versus the silica. And geologists have come up with these designated compositional fields. And so wherever your sample plot's in there, that's, you know, the rock type you're dealing with. So all the red circles are our older porphyritic to aphanitic lavas. You can see that they're plotting pretty solidly in the trachy-dacite to dacite field, so kind of intermediate to evolved compositions. The rhyolites, as expected, plot solidly in the rhyolite field. The mafic lava flows, the younger mafic lava flows that we dated around 30 MA, they're plotting in the basalt to trachy andesite fields. You know, together, the older Eocene rocks form a high K calc-alkaline series. And well, what does that mean? Well, it means it's an acceptable composition for an archetype setting, but it's enriched or high K. You know, a modern sort of classic Andean style volcanic arc would typically, and I'm speaking in generalities here, plot in the calc-alkaline series for reference. So these rocks have been enriched. They're more alkaline than your typical run-of-the-mill subduction zone sort of arc rocks. And then the younger basalts are pretty funky. They're plotting more in the Shoshonitic series, and something that you don't never normally associate with you know, a continental volcanic arc. Okay, so a little bit about we'll look at a little bit at the trace and rare earth elements. Again, not going to dive too deep into this. I'll just draw your eye to the lower left part of the screen here, this where we plotted all the trace and some rare earth elements from all of our older porphyritic to aphanitic lava flows. Whoops, excuse me. And the thing I just want to point out here is that these rocks are generally enriched in what we call incompatible elements. And the sort of camel hump shape that you're seeing is pretty common for a volcanic arc rocks. So no big surprises there. And same with the rare earth elements. We have a pretty steep curve here where we have the incompatible elements on the left and the more compatible elements on the right. And we have this sort of differentiation and steep trend, which is, again, pretty common for volcanic arcs, although this one's a little exaggerated. Not really going to go into that at the moment in this talk, though. The rhyolites have depletions in elements that are pretty common for fractional crystallization processes, and again, they're also enriched. The basalts up here at the top in the green, the rare earth diagram in particular, you look at that has a flatter sort of curve. Again, kind of maybe more characteristic of a basalt associated with in-plate sort of volcanism. So it's, again, kind of strange suite of samples there. So this is what some of these things look like in the field. On the lower left, we have these porphyritic rocks. They're typically massive, a lot of times brecciated. These are probably just effusive, non-violent eruptions. Here's a picture of the aphanitic lavas. They typically have strong flow banding with this really strong foliation and brecciated bases. On the left, the left two pictures are pictures from the Crater Mountain area. These welded tuffs or ignimbrites tend to form these broad tablelands, or at least where they're not faulted and tilted. And locally, they're intercalated with rhyolite lavas. And on the right here, we have pictures from the field of the Avon rhyolite. So these are rhyolite lavas that tend to form these blocky outcrops and have flow foliations. These rocks are highly susceptible to mass wasting. So we see landslides everywhere in these volcanic rocks. And here's a really good example from the Crater Mountain area. So on the right, we have a hillshade, LiDAR hillshade. On the left, we have our interpretation overlaying on the hillshade. And yeah, this is a fairly large landslide with maybe an earth flow associated with it. And so we see these everywhere. Okay, let's move on to the Dillon volcanic field. So this is a photo taken just south of Dillon along the I-15, where it's looking south, and this is the Beaverhead River in the foreground with the Eocene volcanic rocks flanking it on either side in the background there. And this place, this particular area holds a special place in my heart because I'm actually from Dillon, and my dad was a fishing guide on this river. And so I've floated the stretch of river you can see in the photo just countless times as a child. It's me as a kid down there, staring up at these rocks. And so it's been pretty fun to come back as an adult and map them and make some scientific contributions in this area. Okay, so a lot of the work I'm going to show today is in the daily spring 7.5-minute quadrangle shown here. So you can see it's in the middle of a whole mess of complicated geology that Dillon's kind of notorious for. Let's walk you through it real quick here. The purples, grays and purples that we can see here, these are all basement, Archean basement rocks, crystalline metamorphic rocks for the most part, that are billions of years old. And we've been doing some geochronology on those rocks, which has been kind of tough. And then those rocks are overlain by thick sequences of sedimentary rocks shown in the, again, kind of, I guess, blues and greens. So these are Paleozoic through Mesozoic sedimentary rocks that have been all folded up by contractional structures in the thrust belt. And so all the field camps like to take their students here and map those structures. And then locally, oh, I should say we do have some Cretaceous volcanic rocks that we've actually done quite a bit of work on, and that's a whole nother talk in itself. And those are deformed by the contractional structures. And then locally we have these Eocene volcanic rocks shown in red, unconformably overlying these older deformed rocks. And then those volcanic rocks themselves are cut by younger extensional faults, or cut and tilted by them. So I'm going to show you some results from the daily 7.5-minute quadrangle next. So this is one of our state map products. Again, this is the daily 7.5-minute quadrangle, and the Eocene volcanic rocks are shown in shades of pinks and purples here. And so you can see that locally they're overlying the deformed Beaverhead group, as well as Paleozoic rocks that have been tilted and folded by contractional structures. And then the rocks, the volcanic rocks themselves, are deformed by these younger extensional structures. So this is a schematic of the stratigraphy I put together for this area. You can kind of think of it as basically two sequences. We have this lower intermediate to silicic sequence that we dated from about 50 MA to, I don't know, 47 or 48.7 MA or so. And then we kind of get into this intermediate part of the sequence where we still have some andesite, dacite lavas and some intercalated tuffs that are all pretty close in age. And then from there on out, we get into basaltic and rhyolitic kind of bimodal magnetism. So the take home, there's a few take home points here. One is that, the composite section is actually pretty thin, where it doesn't really get over much thicker than 1.5 kilometers. And then we have some younger volcanic units floating around outside the area where I was mapping that we've dated at around 41 MA or so. And we're not necessarily sure how these two groups relate to each other, and we're continuing to work on that. So here's what these things look like in the field. So here's an overview shot. In the foreground, you can see tilted Paleozoic through Mesozoic sedimentary rocks, and then in the background, unconformably resting on those tilted sequences, we have these Eocene volcanic rocks in the reds and darker colors in the background. So here's what the lower sequence looks like. So a lot of you probably recognize this. You've probably driven by it on the I-15 south of Dillon. This is the Pipe Organ rock. I actually dated this outcrop at about 49.6 MA. So this is one of the bottom of the pile. And they're interesting rocks. I think that this might be some sort of volcanic neck or lava dome that we're looking at here. Lots of alteration in the rock, and I should say there's some interbedded tuffs in that sequence too. Here's an overview shot looking at the middle part of the sequence where we have these alternating tuffs and andesite to dacite lavas. There's actually a fault repeating part of the section in here, but They're all erupted in pretty rapid order. And then off on the horizon here, you can see the upper part of the Dillon volcanic sequence in this area where we get into the basalt and rhyolite sort of bimodal volcanism. Okay, so the tuffs have all kinds of flavors in this area, everything from fine grained ashfall tuff to pumice lithic tuffs and ash flows, lots of petrified wood, and then lots of reworking the tuffs locally. So pretty heterogeneity. There's a lot of a lot of these deposits can look quite different from one another, and that made it pretty hard to initially map until we got some returns on our ages. The basalts look like basalts. On the left here, we have a foliated basalt that's overrun its brecciated base. They tend to form these tablelands where they're not tilted anyway, and sometimes have columnar joining associated with them. Here's what the rhyolites look like. So again, you guys probably noticed this recognize this outcrop. This is near Barrett's, across from Barrett's Rock, just south of Dillon, as you go into Beaver Head Canyon. And they're pretty monolithic outcrops, pretty hard to walk around on, actually. And there are some intercalated tuffs in these units as well. And again, these probably represent some sort of lava dome. And then this is from the Dillon West area, where we see really beautiful flow foliations that are folded and really fun to look at. And we don't have any ages back on the Dillon West rhyolite yet. So this is right, there's the hills right outside of Dillon that have the M or whatever, B, I can't remember what the letters are. That all those hills are rhyolite, and we have a bunch of ages pending on those, and we're excited to see if those will be the same as the rhyolite in the photo on the left there. Okay, and then again, we don't have any age dates for these tuffs, but I suspect they're age equivalent to the rhyolites in the previous slide. We have ages pending, just need to get them analyzed. And this is an interesting sequence where we have what I think multiple eruptive units represented here, but probably in pretty tight, pretty rapid interval. And they're capped almost everywhere by this densely welded tuff, like extremely welded tuff. It was probably in place pretty hot and pretty fun and pretty sequence to look at. Okay, a little bit about the major element chemistry. Again, we have a pretty broad distribution of compositions ranging from basalt to rhyolite. These rocks aren't quite as enriched as what we saw in Elliston, but they still plot firmly in the high K calc-alkaline series. The trace and rare earths give a pretty similar kind of camel hump shape on the spider diagrams, and pretty steep rare earth curves. Again, pretty characteristic of archetype rocks. A little bit about structure. I guess I didn't get a good location map. So this is another quad that we mapped recently. It's just north of the quad I showed you a couple of slides back. Shares the southern boundary with that quad. And what we see is that the volcanic rocks are displaced by a series of northwest trending faults. And those are probably related to this Blacktail fault, which we think is quaternary active and active fault. So here's the Burns Mountain and the Daly's 7.5-minute quadrangles I was just talking about in the previous slides. And so those northwest trending faults we're seeing cutting the volcanic rocks are probably related to these active faults. But if we take kind of the broader view, what's interesting about the Dillon volcanic group in this area is that it resides in the footwall block of this big muddy grasshopper detachment fault mapped by Janicki and others. And in fact, when I've been mapping the Dillon volcanic rocks, I've noticed a bunch of sort of intraformational unconformities with units sort of thickening to the east and being tilted to the east as well. And so these I don't know, I suspect that maybe these volcanic rocks could have been erupting during the incipient stages of detachment faulting on the muddy grasshopper detachment, but that's pretty speculative. But this is a good segue to talk about our work on the Challis volcanic rocks over here and the Lemhi Pass 7.5-minute quadrangle. I guess just to orient yourself, Dillon's over here on the far right, got the historic ghost town of Bannock right there. Whoops, excuse me. Grants here. This is the Horse Prairie Basin and the Montana-Idaho divide here. Okay, so a little bit about the Challis volcanic group. This is the geologic map for the Dillon area I showed you earlier. So in the Lemhi Pass area, the geology is a little bit more, a little less complicated compared to the Daly Spur, where we just have Eocene volcanic rocks resting on tilted and deformed Proterozoic belt rocks. So the work we did in this quad was in conjunction with IGS, the Idaho Geologic Survey, and they actually published the map at their survey. So the Eocene volcanic rocks are shown in shades of brown here. Again, they're resting on Proterozoic belt rocks that are shown in green. And these volcanic rocks are tilted and deformed by this Lemhi Pass fault. So here's the stratigraphy we put together for the area. It's pretty similar to the upper sequence that I presented on the Dillon volcanic rocks a few slides ago, but it's missing the lower, so the older dacite lava flows or lava dome, if you will. So what we have is just kind of a more or less bimodal sequence of tufaceous rocks and mafic lava flows that we've dated from 48.6 up to about 46.9 MA or so, 47 MA. And this section is a bit, the composite section here is quite a bit thicker than Dillon, maybe reaching over thicknesses of 2 kilometers. And there are some dacite intrusions around that are somewhat close in age to our dacite dome over in Dillon, and we dated that at around 49 MA or so. And then there are some thin intervals of fluvial conglomerate interbedded in this sequence. So this is what these things look like in the field. These are the mafic lava flows. The tuffs actually don't really outcrop that well. So what we see at Lemhi Pass, a lot of you have probably driven this historic road, following crossing over into Idaho. And what we see is that the mafic lavas tend to form these resistant outcrops, and it's pretty clear when you're out in the field that they're tilted and quite steeply tilted in places. Here's what the mafic lava flows and tuffs look like up close. So in the upper right here, these are all sort of ash ball tuffs that have bedding well preserved, and you can see that they're steeply tilted. And then the mafic lava flows are either sort of flaggy to blocky, and commonly have flow breccias associated with them. Okay, so last but not least, I'll say a quick few words about the Virginia City volcanic field. So now we're going to move over into the pass between the Tobacco Root Mountains to the north and the gravelly Greenhorn Mountains to the south. This is just east of the Ruby Mountains. Alders here for scale. There's Twin Bridges. This is kind of the Beaverhead Jefferson Valley. Down here we have the upper Ruby Valley going into the lower Ruby Valley, and then we got the Madison Valley over here. The surrounding geology is quite complicated for Virginia City, but the Virginia City quadrangle itself is pretty, the geologic setting is somewhat or relatively simple, I should say. So the work we did here was in conjunction with our GWIP hydro program here at the Bureau. So they were working on some groundwater issues with Virginia City and wanted some detailed mapping. So we came in and helped them with that, but at the same time got to work on the Eocene volcanic rocks as well as the basement rocks. And so this is our map that's in review. And the Eocene volcanic rocks on this map are shown in shades of brown. The Archean crystalline basement rocks are shown in green. And you can see that it's a fairly simple map. The volcanic units are displaced by some minor faults, but overall appear to be flat lying. So this is the sort of schematic stratigraphy we put together for this area. The oldest rocks, volcanic rocks, we actually, or I should say Eocene rocks that we found in this area were dacite porphyries. And we dated those around 50 MA, but these outcrops are few and far between, and commonly we found them in landslides. So we're not really sure, and they turned out to be quite a bit older than the rest of the volcanic sequence. So we're not really sure if or how these two sequences are related. And in fact, I'm not even sure if these are intrusions or extrusive lava flows. There just really wasn't a whole lot of outcrop to work with these rocks. From there, the oldest volcanic, or second oldest volcanic unit we found was this Nevada City tuff that we dated at about 41 MA. This is just a fine grain tuff. And then from there, we get into the older gulch tuff that we dated at about 35 MA. And then we get into a big, thick sequence of mainly mafic lava flows with some intercalated tuffs that we dated from about 33 MA. And they're all apparently erupted pretty rapid fire. So here's the chemistry. The older dacite are, well, they're dacite, the porphyries are dacite, and then the older mafic or the younger mafic sequence, trends from basalt to andesite with age. So the older rocks were more mafic, more basaltic, and then the younger rocks trended more towards intermediate compositions of andesite. The rare earth elements yielded a fairly steep curve, definitely enriched, and there were some differences between the older porphyry and the younger basaltic sequences. So here's what these things look like in the field. So the mafic lavas tend to form these broad sort of tablelands that are covered by timber in this photo. These units are highly susceptible to mass wasting, and this is actually a giant landslide complex. You can see just below that tableland. Looking closer at the mafic lava flows, they tend to form these benchy sort of outcrops. They're pretty easy to recognize in the field. When you take a closer look at them, they can be blocky to flaggy with well-developed flow foliations, and almost all of them have some sort of flow breccia associated with them. Starting to see a trend here. Let's see, the tough rocks aren't very well exposed, and it doesn't really get much better than this, unfortunately. Let's see, so like I said, these rocks are highly susceptible to mass wasting and landsliding, and we had money in this project to get some LiDAR flown, and so this is a swath of LiDAR we had flown. This is for reference, this is Alder Gulch here. Virginia City is located right here. Here's Granite Creek, and you can see that there's just some monster landslide or earth flows in this area formed in the volcanic rocks. And what of interest to us is this landslide perched above Virginia City. You can see the streets of Virginia City in the LiDAR image here. I should say this is a hill shade of the LiDAR data. And I suspect that actually this landslide underlies Virginia City, meaning that Virginia City is built on a landslide. And what it looks like, what's going on with all this landsliding in this area is that you basically have a pretty thick sequence of mafic lava flows that are pretty coherent, pretty dense, that form a pretty dense coherent package. And those are resting on weak, unconsolidated, fine-grained tuff deposits. And so we think that we have these big landslides, initiating or failing in that tuff deposit, or those underlying tuff deposits forming. In this case, I interpret this to be more of a rotational sort of landslide with maybe some earth flow at the toe. Okay, so let's get into some conclusions. I think I still have some time here. We started, I think, 10 minutes late. So I just want to do a synthesis of the data from these volcanic fields I've discussed today. And first, I want to talk about the tempo of volcanism. So in this plot here, I've plotted all the age data that I've presented today from these volcanic fields. So we have about 65 ages, and most of these are uranium-lead ages, and about 3 of them are argon-argon ages. And I've plotted their locations here. I should say I included a few ages from the Hog Heaven. I've been working with Caleb Scarberry and Ethan Kopiage on that a little bit. I had them at hand, so I threw them on this plot. Anyway, when we plot up this data, so I've just sorted it by age here, and you see the data seems to be forming these sort of discrete intervals or pulses of magnetism, if you will. And I don't know if this is real or sampling bias. I mean, I feel pretty confident that we've done a pretty good job of dating all the volcanic units that we can, but we don't quite get all of them, mainly because it's hard to date some of the finer grained mafic intervals that are altered. But nonetheless, I think that this trend we're seeing here is real. Now, what these pulses of magnetism mean, I don't know, but I think these might be real. at least of what we're working with the preserved rock record. So how do these ages look spatially? So what I'm showing here is I've plotted these ages versus latitude on the upper plot, and then versus longitude on the lower plot. And if you look at this lower plot or this upper plot, I'd argue there's really no coherent trends in the age distributions of these rocks as we go from south to north. So north is up. And if we look at this lower plot, where I plotted the data versus longitude with east to the right, again, I'd argue there's really no strong trend in the age distribution for these volcanic fields. So bottom line, no north or south sweep, no west to east sweep that we can see in Montana with these particular volcanic fields anyway. Let's see, let's look at the alkalinity of the rocks. And so the ratio of potassium to silica is a good sort of alkalinity indicator. And similarly, I've plotted that ratio versus latitude on the upper plot here. And again, I'd argue that there's really no strong trends other than Elliston. Yeah, it looks like it's shifted a little bit to you know, the ratio is a little bit higher, a little bit more alkaline. But overall, they're all, I'd say they're all, you know, pretty high K, as we saw in the plots I presented earlier in the talk. Similarly, if we look at longitude versus this this alkalinity indicator, I'd argue we don't really see any strong trends or no strong west to east sort of sweep, and same with north to south. So we can look at the tantalum-cerium ratio as sort of a tectonic affinity indicator. So again, similar to the previous plots, I've plotted them, this ratio, latitude versus longitude for these samples. And again, you know, not too many strong trends. It is interesting that the Elliston seems to have a little bit lower ratio. So I should say that, you know, values of less than 0.001 are pretty consistent with modern sort of volcanic arcs, where values above 0.02 are kind of more consistent with what we call within plate magnetism. And so a lot of these samples are actually kind of in that in-between, or trending in that in-between zone. Elliston kind of plots firmly more in the volcanic arc realm of things. But overall, I'd say that, again, not any super strong correlations, spatial correlations at this point. So do a little bit of hand waving with one of the tectonic models I presented earlier. First, I'll say that the data from these 3 small volcanic fields is not really definitive of anything, or doesn't really allow us to make too many sweeping grand conclusions about the tectonics. But I will say that the slab window model by Brett Sprecher does a pretty good job of accounting for the alkaline volcanism in southwest Montana. Remember, keep in mind, a lot of these volcanic fields are enriched or high K calc-alkaline in nature. So if we plot their slab window model on this map, so the blue lines is showing the outline of the slab window, so the slab window would be between the 2 lines. You know, we see that at 50 MA, that slab window is positioned right under the Challis and Absaroka volcanic fields, which are really large volcanic fields. And then by 49 MA, that slab window seems to shift a bit, and is centered more on the Elliston area, and as well as the Sluice and Clark line, and might have been driving dextral shear and the overriding crust in this area. It's kind of an interesting thing to think about. Okay, so conclusions. All the volcanic fields I talked about today, you know, comprise a wide array of volcanic rock types that generally represent high K calc-alkaline magmatic assemblages. The bulk of the Dillon, Challis, and volcanic rocks were erupted between 52 and 40 MA, whereas the Virginia City rocks are a bit younger. They're erupted at 35 to 33 MA. You know, the eruptive units, generally speaking, seem to become more bimodal with time. And at this point, there are no spatial trends in compositional and age data that I can detect anyway. So on continuing work, Katie McDonald and myself have been mapping the Burns Mountain, Dillon West, and Gallagher Mountain quads the past couple of summers, and we have a whole slew of ages in the works, or I should say uranium lead ages and geochemical analyses that'll really really help us paint a more clear picture of the volcanism in the Dillon volcanic field. And we're actively compiling all the published age and geochemical data from Montana, both what we have in-house, but also what's in the literature, so we can do a better job with this sort of regional synthesis that I touched on in my conclusions here. Okay, and so with that, I'll open the floor to questions. I guess first I should thank all the people that have helped me. I've had a lot of help since I started here. First off, I just want to thank my mapping colleagues that helped me on these projects: Katie McDonald, Susan Book, Colleen Elliott, Jeff Lawn, Reed Lewis. I've had a lot of help in the mineral separation lab with Stuart Parker, Connie Thompson, Katie McDonald, and Gary Weiss. Andrew Kylander Clark is a good friend and colleague at Santa Barbara that runs the ICP-MS facility there, and he's been really helpful and instrumental in this work. We send our geochemistry, our samples for geochemistry work at WSU, and Charles Knack, Ashley Steiner, and Scott Burrows have all been a lot of help with our samples. The argon, Jake Ross and Matt Heisler helped with the argon dating. Andy Bobson and Jeremy Crowley were instrumental in collecting the Virginia City LiDAR. And we have a lot of GIS and cartography support from Paul Thale, Susan Smith, Ewan Lee, and Chris Smith. And last but not least, Finn and Pippi are helping me a lot in the field, give me a lot of companionship. So with that, I'll open the floor to questions. If there's anybody still there. Hello?
We're all still here.
Okay.
So people who have questions can either just raise their hand or turn on their microphone and ask them.
It's Colleen here. Can I ask a question?
Yeah.
Just diving down into the heavy duty nitty gritty. First of all, awesome talk. That was really interesting. Nice. It really puts things in perspective for me. And no sweep. There's no sweep, right?
Well, I did have, I tried to cram a lot into this talk, so I had to delete some slides, including one that had a lot of caveats on it. And this was just me throwing my data into Excel and playing around with it. And, we're looking at, actually, am I still sharing a screen here?
Yeah.
I should pop this back up. But, I'm looking at a tiny part of the Challis, not even, you could almost argue it's not even really the Challis. And then Dillon, Virginia City, and then Elliston, which I guess is a pretty good look at the volcanic rocks in this region. But before we make any sort of definitive or sweeping conclusions, I definitely want to get this compilation done and include data from all the volcanic fields and, in Montana and the surrounding states, and maybe even more regionally. But for this talk, I just focused on what I've worked on so far.
Well, so you know my preconceived biases here, so
yeah,
that's okay. But it's something. I know this is going to be a stupid question, but the geochemistry of all these volcanics, it looks very arc-like, but it's hard to ignore the connection between the timing of volcanism and the timing of extension on the core complexes.
Oh yeah, for sure. Yeah, and well, anyway, sorry, finish on with your.
No, go ahead.
Yeah, no, I agree, and I think there probably is a relationship there, and what's interesting too is when you look at the magnetism in the core complexes, there's Eocene magnetism actually in the core complexes themselves. Tends to be a bit older, I guess, around, I can't remember the numbers off the top of my head, but Eocene. And I definitely think that there's a relationship there. I don't know if it's, it's kind of the chicken or the egg problem that it's recycled over and over in the literature, but is one driving the other, or are they just both occurring contemporaneously due to the changes in the tectonic parameters, or like all of the above? But there does seem to be both a spatial and temporal relationship there for sure. And
And would you not expect to see some geochemical sort of relationship to extensional tectonics or not?
yeah, maybe, but I think the problem here is that we're, this magnetism is like right on the heels of pretty prolonged, subduction and potentially enrichment of the overriding crust. And so, I guess it just all depends on how the melts are forming exactly. But, I guess that figures way back at the beginning of the talk. But when you read about this in the literature, a lot of people in their tectonic interpretations just talk about how, prior to Eocene magnetism, we had this long-lived subduction going on and potential, and especially during flat slab subduction, potential enrichment of the sort of lower lithosphere, if you will. And so a lot of that sort of signal we're seeing in the chemistry might be more related to previous subduction than what's happening during the Eocene, if that makes sense. But what's interesting about the younger, I know this, the younger, the kind of mafic lava flows that have those shoshinitic sort of compositions, those are really strange compositions, and those are erupting around 30 MA. So maybe those are coming up along, fault systems or fault zones and are kind of tapping a deeper, more primitive melt source. But yeah, those are kind of outliers. So yeah, I don't know if you have ideas of clever ways to tease out this extensional, signal in the chemistry. I'm sure people do it, and I'm not aware of it. But yeah, that's something I'd like to look into, because I do think that there's a relationship there.
So Jesse,
Yeah.
One of the things I noticed from sort of one of the regional maps, or two of the regional maps you put up, is that the volcanic areas that you've looked at are in or south of the Lewis and Clark line.
Yep.
But on the Montana map, there are two kind of out of context volcanic places. The what's it called? The Bear Paw and the
highway
mountains. And I've been to both of those.
Mm-hmm.
Of course, I'm not really a geologist, but they're just so bizarre. That I was wondering, sort of, if from what you've learned and the ones you've looked at, do you have any hypotheses or conjectures regarding anything about the bear paws or the highwood?
That's probably more of a question for Dick Berg. But yeah, no. So that's part of what we call the the Montana alkalic province. And you're right. They have weird compositions. They're really alkaline, as their name implies. And again, people kind of argue back and forth on, what these rocks, how are these rocks actually formed? And this kind of comes back, one of the ideas coming back to what I was just talking about is that, one way people like to explain the calc-alkaline province is through flat slab subduction, where, you have this gently dipping slab that, for one, allowed you to have magnetism and volcanism very far away from the active, trench or subduction plate margin, I should say. And so the idea is there that maybe through longer term flat slab subduction, you just had enrichment of that overriding crust in that area that formed those rocks. But I don't, the person to ask that question would be Dick Berg. Maybe he has some things, I see he's on here, maybe he has some things to say about it. But yeah, I actually don't know a whole lot about those rocks.
Dick, are you gonna propose some answers, or? I guess not. Are there other questions?
I guess I have a question, Jesse.
Yep.
Really like that talk, and So are people thinking that there was flat slab subduction north of the Lewis and Clark line up into BC?
Yeah, you know, I'm not sure about that. Maybe Colleen knows. I've been so focused on Northwest US. I've never, yeah, I don't know off the top of my head, Chris. Why, what
Okay.
do you want to know? Or what do you
Well,
think?
if the Lewis and Clark line is some sort of boundary between where a downgoing slab kind of split, and some of it went flat and some of it stayed steeper.
Right.
Um,
And you
but
know, that's something like we see in the modern Andes, where you have segmentation of that downgoing slab, and you know, simultaneously you have flat slab and sort of steeper dipping segments
okay.
occurring along the plate margin. So it's definitely a possibility.
And is there zones like, I mean, you know, and then maybe there's zones like the Lewis and Clark line down there along that border. I don't know.
Yeah, you know, like it wouldn't surprise me, like where I actually worked pretty close to one of these sort of hypothesized zones for my PhD work. And, you know, it's sort of the map scale. They didn't have much really mapped, but a lot of the mapping could use, you know, is fairly coarse. So it, you know, it could be there.
Thanks. I just had to cough. Good talk.
Great, yeah. Great talk. Any more questions? So thank you all for coming. Please, if there's more than one person watching with you, send Victoria either a text or a chat or an email so that we have an idea of how many folks were benefiting from Jesse's insights and data. A lot of field work really went into that. And let's give him a round of applause.
I'd also like to chime in. Can you all hear me?
Yep.
This is Madeline Godkwitz, and I apologize for my technical glitch at the beginning of Jesse's talk, but I did want to acknowledge the significant contribution that Jesse's made to the Bureau and the mapping program in developing the mineral separation lab facilities and in really bringing that ability to date rocks up to a whole new level here at MBMG, and the significant impact that's had on our ability to do so well in the annual awarding of federal funds for geological mapping. So really a big shout out to Jesse for being both dedicated to that idea and diligent in carrying it out and developing that lab. So thanks, Jesse.
Oh, thank you.
Thank you. Let's give him a round of applause. Doesn't work quite so well. You can use your reactions in Zoom. So thank you all so much. I'll remind you that we've been recording this session, and with Jesse's permission, it will be available through digital comments on Montana Tech. And thank you so much. It was a great talk.
Thanks, Bev. Thanks, guys.
Do you need to make Victoria the host again so that she
No,
can?
I think I got it. I'm just exiting out, and I'm going to hit end now. So thanks again, Bev.
Thanks. Thank you.
And thanks, Victoria.
Anytime. Thank you, Jesse.
All right. See ya.
Bye.